Today we're going to be talking about even and odd functions. This is kind of supporting the activity y'all did today on October 3rd, or maybe today, October 4th, depending on when you are seeing this. So even and odd functions are just a good way to look at what are called the symmetries of a function, given a chart, graph, or even using some common algebra. So if you were kind of unfamiliar with what was going on during the activity today, hopefully this will clarify some of these ideas. So we're going to be looking at an even function, an odd function, and a neither function, and actually seeing how we can see these symmetries from a chart to a graph, and finally looking at the overall equation. So let's start off with an even function. When we're looking at an even function, we're looking for a specific type of symmetry. We are looking for a symmetry over the y-axis. Or we're looking for similar y's given the fact that we walk over in both directions, we'll get the same exact y. And so a good example of this is going to be y equals x squared. So the first thing I want to do is really look at the chart of this and then we'll come back to it after we see the graph, to kind of decide what makes this an even function and where this symmetry is coming from. So we can make our xy table. I'm going to choose values between -2 and 2. -1, 0, 1, and 2. So I'm finding my y values from here. I know that when x equals -2, well, this rule says square your input. So our output y is going to be -2 squared, or -2 times itself, which gives us a +4. So when x equals -2, y equals 4. We can translate that into a point on a graph by saying, all right, the x represents our input, the y represents our output. So we do the same thing with all our other values. So -1 squared is 1, 0 squared is 0, 1 squared is 1, and then 2 squared is 4. So if we graph this out, we should get a very familiar shape. So we have our negative, we go backwards 2 steps, we're up 4 steps. We go backwards 1 step, we're up 1 step. We're sticking at the origin, over 1, up 1 for 1, comma 1, and if our input is 2, our output is going to be 4. So if we did all the in-between spaces, we'd get a function that looks like this. So the graph is kind of the most obvious way we can see this symmetry. If we look at our y-axis right here, notice how we could fold this thing in half and we would have this side directly overlapping this side. When we have that, that's what an even function is. And so that's what we mean by symmetry over the y-axis. It's saying that our graph can fold over perfectly along the y-axis. In this case, this is going to be our y-axis, right? So another way we can see it is by actually looking at our table. So if we take a positive step, or we look at x equals +1, we should get the same exact output as if we looked at x equals -1. So when we're looking at our chart, notice how on both the positive and the negative case, we get the same exact output. Okay, we can also go to -2 and 2. Notice how putting a negative in place of our x is going to give us a positive output, both being 4. So that represents that symmetry. It's saying we can step 1 unit in either direction and get the same exact output. Step 2 in either direction from the origin, we get the same exact output. So if we wanted to do this by algebra instead, the general rule is that for an even function, if we put in a negative x in place of the x, our function, our outputs are going to be the same exact values. So we put in an x, for example, we put in a 1, we'll get out a positive 1, so our f of 1 will be 1. But if we put in a negative 1, we'll also get a positive 1 out. So we can see that in a specific example like x equals 1. If we look at f of 1, well, that's the output when the input is 1, so that's just 1. But when we look at f of negative 1, well, that's just negative 1 squared. Or, looking at our chart, it's again 1. So we've shown here that our output for negative 1 is the same exact as it is for 1. So we can say, at least for this specific point, it's pointing towards an even function. If we wanted to take into account all x values, say we wanted to compare x equals 1,000,000 to x equals negative 1,000,000, if it's an even function, they should both come out to the same exact value. Well, we can just look at our single x, so let's do a general case. So we're going to just leave it as x, so f of x is equal to x squared, our function, but our negative x, well, we're just replacing what our value was with the negative of it. It's just saying any number I wanted to put in, I'm going to check out the negative version of it. And we know that if we have f of negative x, that's just negative x squared, or negative x times negative x. Well, you multiply two negatives together, you get a positive, and you get the x squared at the end. So we can see that f of x gives us x squared, f of negative x gives us x squared, so these two guys are actually equal to each other, and by our definition up here, that means that this is an even function. Okay, so even. So that was a pretty in-depth explanation. For the odd functions, I'm going to glaze over a little bit, but hopefully it'll be enough information to get a good understanding of this. For this example, when we're looking at odd functions, we are going to look at y equals x cubed in this case. So for an odd function, we're not just looking for a symmetry over the y-axis. We're trying to find out a function where we flip it over the y-axis, and then we flip that piece over the x-axis, and then we should have that perfect overlap. So an odd function reflects over the x and y-axis. So what that means for, in the case of a chart, well, we'll actually get to that part. Let's just focus on graphing it out first, seeing that visual, and then we can get a little more abstract with it. So we're going to be looking at y equals x cubed. We'll create our chart again, x, y. I'm going to use the values between -2 and 2 again, so that we can see that pattern. And so we do -2 cube it, -2 times -2 times -2, that's going to give us a -8. -1 will give us a -1, -1 times -1 times -1, 0 will give us 0, 1 will give us 1, and 2 will give us 8. We can graph this thing out. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And then maybe 1, 2, 3, 4. 1, 2, 3, 4. Great. So we start off with our -2. We're going to go all the way down to 8. -1, we're at -1. 0, we're at 0. At an input of 1, we're at an output of 1. And at an input of 2, we're at an output of 8. So this cubic function is actually going to be a great example of our odd functions. If we're looking at just the way that we've defined it graphically, it says that we're trying to take this part right here, and we're trying to reflect it twice. And if we can reflect this over the x-axis, or over the y-axis, and then over the x-axis, or vice versa, flip it over the x-axis and then the y-axis, we should end up with this, with our function looking like this. So we flip this upside down, we'll get something that looks like so. I'm just going to kind of give that in-between step. And then notice after we flip it upside down, we can flip it to the left, and we have that perfect overlap on the other half of our function. So what that means in general is that the output of a positive x value is going to be the negative of the negative input. Or in most general, and I'm going to write this on the other page too, for the algebra side, if we put in a negative x into our function, that's going to be the same exact idea as looking at the negative of that value x. And over here, I'm going to squeeze it in, and then we can do the most general on the back page. But what this is saying is, for example, if we are looking at our function at 2, at -2, that should give us the negative output of our function at +2. So if we're checking out +2 first, we can check our chart and notice, okay, well, we put in a 2, we get out an 8, so this has to be 8. And then we try it with the negative. We look at our -2, and that's going to give us a -8. So notice how if we step backwards 2 units, we're actually going to get the negative value of if we stepped forward 2 units. So because f of -2, 8 is equal to the negative of the positive, which is 8 right here. So notice how they're changed by signs. We can say that this is an odd function at least for 2. But we want to be the most general. We want to know for every single positive stepping stone, we're going to have the negative give us the negative output. So in that case, we'll do the algebra approach to see this. And so if we have, again, our y is equal to x cubed, we're going to want to try the positive, simplify it, and see if it comes out to the negative of what we have elsewise. So if we have y equals x cubed, we know that f of x is going to give us just that plus x cubed, or x cubed. So if we try to put in a negative value now, say f of -x, well, if we cube a negative value, we still have a negative left over. That's like saying -x times -x times -x. So here we have 2 negatives make a positive, another negative will make the whole thing negative. So here we get -x cubed. So we're comparing this guy to this one right here, and notice how the difference is that overall sign. So because we know f of -x in general is going to give us the negative of our function right here, we know that we have an odd function on our hands. So I want to go through a little bit more complicated of an example of odd because that sign can sometimes be a little hard to identify, and then we're going to look at the kind of boring case of just generally having having neither happen, neither even symmetry or odd symmetries. So for example, we'll just do another odd symmetry. So something like f of x, I'm going to go to function notation now, is equal to, let's say, x to the 5th plus x. Okay? So what we're trying to do is figure out, in general, what is this function going to look like when we have a negative value in here? So we're going to instead replace all our x's with a negative x. So what used to be an x is now a negative. And then what used to be this positive x, we're replacing it with the negative of that value. That's just like back here when we were saying, okay, what does the output come out when we do the negative of our 2? Or in the even function case, what happened when we put a negative 1 in there instead of a 1? So same idea, but we're just making this more general by saying, now let's look at any number. So we can expand this out. We have negative x times negative x times negative x times negative x times negative x. And then we finally have that last negative x added on. So any negative to the odd power is going to give us a negative. These two cancel. We're left with a negative still. So we have a negative x to the 5th. Next up, we're dealing with this other x, so minus x. So what we should notice is that we can actually distribute out or pull out a negative sign from each. This is like saying negative 1 times x to the 5th plus negative 1 times x. If I pull out a negative 1 from both of these, we'll see that we actually have our original function in there, our f of x. So let's just replace this with what it's represented by, f of x. And so that way we'll get negative 1 times our original function. So we've shown here that our negative x, and so every single time I can just bring this down, f of negative x, this is what this represents, this is what it represents. So finally we've shown that when we plug in a negative value, any negative value, it's going to be the output's going to be the negative of the positive x. So this shows that it's an odd. And the big thing right here is that we were able to distribute the negative out of both. So neither is the last case we look at, neither. That just says there's no symmetries. No symmetries. And all that's saying is we can't really fold our graph either way. We can't find any nice symmetries when we look at 0 on our chart and take a step over. There's no pattern like we kind of see in these two charts. Something, example of this would be like, so no symmetries on the graph. And no real patterns around x equals 0 on a chart. So a good example of this would be like x squared plus x. F of x equals x squared plus x. So if we were to graph this thing out, it would be a parabola. I'm just going to sketch this to show that there's no symmetries, because remember, it's over the y-axis or the y and x-axis. So this will give us a parabola that's kind of hanging out over here. And so notice if we cut out, so here's our parabola. If we cut out this part and we tried to reflect this over the y-axis, we're not going to get something like this. Notice how this reflection looks nothing like this. So it's not going to be even. If we take this and flip it upside down, like so, and then try to reflect it over, well, that's definitely not going to be a reflection either. So we can see it in the function itself. We can also see it by centering our chart around 0. 2, -1, 0, 1, and 2. So in this case, 4 minus 2 is just 2. So 2 squared is 4, minus 2 is 2. -1 squared, that's +1. Minus 1 is just going to give us 0. 0 is just going to give us, -1 squared plus -1. 0 squared is going to give us 0 as well. 1 squared plus 1 is just going to give us 2. And 2 squared plus 2 is going to give us 6. So there's almost some sort of symmetry around here, but notice how if we treat our 0, 0 as kind of our line of symmetry, there's no connection between the outputs from the 1 step and the 2 step. So notice how our values are completely different. Another way we can see this is by trying to do the algebra test for each. If it fails both algebra tests, if both algebra tests fail, that's also a good way to notice that this is not going to, you're going to get a neither. Okay. So we had 3 different rules. We had even functions, which we can see by the chart. If you hang tight at 0, step in either direction, you're going to get the same output. Or more generally, you're going to have the fact that plugging in a negative x value will give you the same exact output as a positive x value. We can show that in general. We showed it during an equation. Odd function, we can reflect it twice. Or if we're looking at our chart, we'll notice that if we step over one direction or one unit in either way, we are going to have the negative for each one. And we can see in general for the algebra, we're looking for this relationship between the two, which we showed for the example of x cubed right over here. Okay, and then finally we did a harder one, remembering we can also check by distributing on a -1. And finally for the no symmetry, we find that, and I actually encourage you to try the even and odd for this function, showing that you're neither going to get this result or the even function result.